Hi and welcome everyone. This lecture, I want to go over symmetric matrices and orthogonal diagonalization. So let's first go over the definition of a symmetric matrix. You have a symmetric matrix if A equals to A transpose. That means when you change the rows and the columns, you get exactly the same matrix. And their properties to symmetric matrices, if we have an n by n symmetric matrix, first of all, A is diagonalizable, and we'll see why. All eigenvalues of A are real numbers, and I will do the proof for this with a 2 by 2 matrix. And if lambda is an eigenvalue of A with multiplicity k, then lambda has k linearly independent eigenvectors, and that's very important. For example, I put a note here for you. If you get the characteristic equation and you have lambda minus 1 times lambda minus 2 squared, your first lambda is 1 and the multiplicity is 1. The multiplicity is just the exponent of that factor. Here, lambda 2 equals to 2 and the multiplicity is 2. So what we have here is a repeated rule, and not all the time when you have a repeated rule, you get two independent, linearly independent eigenvectors for that lambda, but that's always the case for symmetric matrices. Now, the proof we have here for a 2 by 2 symmetric matrix. So I just want to show that this last note I wrote here, but that's only for a 2 by 2 matrix. For an n by n matrix is not in the scope of our class, but the question is, when we have a symmetric matrix and we see clearly this is symmetric because A is the same as A transpose, is this diagonalizable? So it's diagonalizable when we have two distinct real lambdas for the characteristic equation. So let's write that. The characteristic equation is lambda I minus A, the determinant of that matrix, which is that this is a 2 by 2 matrix. The determinant is just that times that minus that times that. So it's lambda minus A times lambda minus B minus C squared. And if you simplify that, multiply, did you get you get that expression. If you just combine like terms, that's what you get. This is a quadratic equation. So this is our A, which is 1. This is our B, and that's our C. Now, to kind of see what we have, what type of solutions we have, we can directly go to the discriminant. Like that's called beta, which is base squared, b squared minus 4ac. So this is just, we're using the quadratic formula, but the discriminant part, let's see what we get. So we said our b is a plus b, so it's a plus b squared minus 4 times a times ab minus c squared. Now, if you simplify that, you get a squared minus 2ab plus b squared plus 4c squared. That is just a minus b squared and plus 4 times c squared. And as we know this is the sum of two squares. That's a squared and plus 4 times, or even you can say 2 squared here. And this is always positive. Well, positive, or it could be 0. So we know the discriminant is never negative. So it could be positive or it could be 0. First case, if the discriminant is positive, then the characteristic equation has two distinct roots, or two distinct real roots, we can say. And if A equals to B, this is going to be 0 and C is 0. So we get 0. If delta, that case, delta equals to 0. But if you write the matrix, we know C equals to 0, and you can put A and A here. Let's take a look at our matrix. So this becomes 0, and these are the same. And we get a diagonal matrix which is diagonalizable. So now let's talk about orthogonal matrices. For symmetric matrices, we set A equals to A transpose. But if the matrix is orthogonal, then A inverse equals to A transpose. So remember that. Now, when we diagonalize a matrix, we said we can have a diagonal matrix such as we can write that as P inverse times A times P. When we diagonalize A, that's what we can have. But let's see, for symmetric matrices, the matrix P can be chosen to have the special property, and that's the special property, which is P inverse equals to the P transpose. In this case, P is said to be an orthogonal matrix. So for example, these are just a couple of examples of orthogonal matrices. So in this case, we have a matrix 2 by 2 matrix. If you find the inverse of this matrix, it's going to be exactly equal to P transpose, and same as this one. So try to do this. We learned how to find the inverses and the transpose of the matrices. Try it for this matrix and try it for that matrix and see if the inverse equals to P transpose, and it will be. Now, another property of orthogonal matrices, if we have a square orthogonal matrix, is an orthogonal matrix, let me read that, if and only if its column vectors form an orthonormal set. Orthonormal set means the dot product of each vector in that set will be 0, and the dot product of the vector by itself in that set will be 1. So let's go over the proof of that. Let's say we have, assume this is an orthogonal matrix and these are the columns. So if I write the columns, we can write P11, P21, and so on, and P12 up to Pn2, and P1 and up to Pnn. So these are the components of those vectors. You write it as a matrix. If you multiply P transpose times P, so we get that matrix. So if you do the model, find the transpose of the matrix is just P1 dot P1, P1 dot P2, and so on, P1 dot Pn. But that's the same thing as saying P inverse times P. We know that the inverse of a matrix times the matrix itself is going to give us the identity matrix. So what's going to happen? All the diagonals are going to be 1, and everything else, all these are going to be 0. Now let me go over that. I explained that slowly here. If we have a set of vector, this is an orthonormal. If Pi dot Pj will be 0 if I is not equal to j, and will be 1 if I equals to j. So when we multiply P transpose times P, that's the same thing as P inverse times P. We do get the identity matrix. And as you notice, the diagonal is always Pii times dot Pii. As if I go back, you can see all these numbers are the same. So conversely, if P is orthogonal, then the reverse steps above verify that the column vectors of P are orthonormal, form an orthonormal set. What do I mean by that? If you take this matrix, this is an orthogonal matrix, we already know. If you take the dot product of P1 times P dot P2, you get 0. P1 dot P3 is going to give you 0, and P2 dot P3 is going to give you 0. Please try that on your own. And if you do P1 dot P1, you're going to get 1. So, and I put it, that's going to work with this matrix, pi dot pj is going to give you 0, and pi dot pi, or if the same I equals to j, is going to give you 1, and the magnitude of each column is 1. Please try that and check that. Going back to symmetric matrices, again, symmetric is when A equals to A transpose. So if you have a symmetric matrix, lambda 1 and lambda 2 are distinct eigenvalues. If they are distinct eigenvalues, then the corresponding eigenvectors are orthogonal. So for any symmetric matrix, if the lambda 1 are distinct values, then the corresponding eigenvectors are going to be orthogonal. So for sure, you can try for the first matrix, but let's go over the proof of that. Let's say we have lambda 1 and we have x1 is the eigenvector, we have lambda 2 and we have x2 is the eigenvector for lambda 2. Lambda 1 are not distinct eigenvalues. If I write the relation, you know that a times x1 is lambda 1 times x1, a times x2 is lambda 2 times x2. I just want you to know this property. When you do the dot product of two vectors, you can also write that as matrix multiplication. That means the transpose of the first one times, this is not dot, the second vector. So, and I try to show that here. Let's say we have vector x1 and the vector x2. These are the components, these two vectors. x1 dot x2 is x1 y1, x2 y2, and xn yn. If I write this as a matrix notation, so you can just do it that way. And if you take the transpose of that, which is x1, x2, so you can write it as a column vector, and times the times x2, which you write it as a matrix notation also, will give you exactly the same thing. So x1 times y1 plus x2 times y2 and so on. So the dot product can be written as a matrix multiplication when you take the first matrix and take the transpose of the first matrix times the second matrix. Now let's start with this relation. We can start with lambda 1 times x1 dot x2, and using the associative property, we can say this is lambda 1 x1 times dot x2. This is, but lambda 1 x1, we showed that it's a times x1 dot x2. And we know that we can take the transpose of the first matrix and do the matrix multiplication here. But the transpose of two matrices, the product of two matrices, can be written as the transpose of the second matrix times the first matrix. Just check the property of one of the properties of transpose matrices. So you can write that as x1 transpose times a transpose times x2, and that's x1 transpose times a, because a transpose is just a. We assumed it's a symmetric matrix, and you can write that times x2. Now you can write this as x1 transpose times ax2. But what is ax2 from here? You know that ax2 is just lambda times x2. And finally, you can write this as x1 times x1 dot lambda 2 times x1. Take it back to the dot product. And as you notice, we started from here, lambda 1 times x1, no, lambda 1 x1 dot x2 is the same thing as x1 times lambda 2 times x2. So what's the conclusion? 1 is the same thing as 2. So if we write that, so this is the same as this one, and you can probably here add, so you can say this is the same thing as lambda 2, and that's times x1 dot x2, and that's our number 2. And we take number 1 and put it equal to number 2, and if you take this one to the left side, you get 0. So this quantity is 0. If you factor out x1 dot x2, you get lambda 1 minus lambda 2. We know these two are not, they're distinct real numbers because it's symmetric. They're not equal to each other. So for sure, x1 dot x2 will be equal to 0. Therefore, you can say that x1 is orthogonal to x2. And again, our goal was to prove, if I go back here, if lambda 1 and lambda 2 are distinct eigenvalues of A, then the corresponding eigenvectors x1 and x2 are orthogonal. And we did see that the dot product of these two vectors gave us 0. So an example of that, this is a small example. If you have a matrix that's symmetric, if you find the eigenvalues, you get 2 and 4. I didn't go over the work here, but I'm sure you know by now how to find that. If not, watch the video how I find the eigenvalues, the characteristic equations. Then you can find the eigenvectors. The first one is going to give you that, and the second one is going to give you that. And these are just numbers, and if you do the dot product, you are going to get 0, and that works for every symmetric matrix. Now we learned about symmetric matrices and orthogonal matrices. Let's talk about orthogonal diagonalization. If you have a square matrix, that matrix is orthogonally diagonalizable when there exists an orthogonal matrix P such that you can write that relation. But this is symmetric and this is orthogonal. So fundamental theorem of symmetric matrices. If you have an n by n matrix, then A is orthogonally diagonalizable and has real eigenvalues if and only if A is symmetric. So in order to orthogonally diagonalize a matrix, that matrix has to be a symmetric matrix. The proof of that, so we know when we diagonalize, you get this. We have a diagonal matrix such that we can write that as P inverse times A times P, and P inverse is equal to P transpose. So if I write A now, so I can write A as P times D times P inverse. That means if you take this and multiply both sides by P and P, then you get the PD on the left side, and if you multiply by P inverse and P inverse, this is just I, then you can isolate A that way. So A can be written, if D can be written as P inverse times A times P, then A can be written as P times D times P inverse. But we know that P inverse is just the transpose of P. The transpose of A is the transpose of that matrix. But the way you can write the transpose, AB transpose is B transpose times A transpose. So here you can take this and write the transpose of the first one, the transpose of the second one, and the transpose of the third one. So this is a property of the transpose of matrices. So now P transpose is just P. D transpose D is a diagonal matrix, so it's just D. The transpose of a diagonal matrix is itself. So we have P times D times P inverse, because P transpose is P inverse, and that's going to give us A. So we started with A transpose, and we end at B, A. So therefore, A has to be a symmetric matrix. Orthogonal diagonalization of symmetric matrices. So there are some steps the way you do it. So you are going to be given a symmetric matrix. You can find the eigenvalues of that and determine the multiplicity of each. For each eigenvalue of multiplicity one, find a unit eigenvector. So normalize it because they have to be, the columns have to be orthonormal. So normalize that for each eigenvalue of multiplicity k greater than or equal to find a set of linear eigenvectors. If not orthogonal, then you have to apply the Gram-Schmidt orthonormalization process and find an orthonormal basis. Now you take the result in number 2 and number 3 and produce an orthogonal set of n eigenvectors and use these eigenvectors to form the columns of P. So if you know, on the last video I did the diagonalization, so the process is the same. So you just have to here use the normalize your vectors or just use the Gram-Schmidt process. For a 2x2 matrix, just note this is a symmetric matrix. If you find the eigenvalues, you get -3 or 2. Finding the eigenvectors, you have to do the row reduction, get the RREF. So for this first one, you get -2 and 1. And the second one, if you do the row reduction, you get 1 and 2. Then this is not enough. So first of all, we know they are orthogonal to each other, but you have to normalize each one. So you normalize the first one, and the norm of this vector is square root of 5, and you get that, and you normalize the second one, and you get this one, and double check if you find that you multiply P inverse times A times B, you are going to find the diagonal matrix where the entries on the diagonal are going to be -3 and 2, and please do that on your own. So in summary, when you have an orthogonal matrix, let's call that Q. It's an n by n orthogonal matrix. Q times Q transpose is Q transpose times Q, and that's I. We know that Q transpose is the same as Q inverse. The columns of Q form an orthonormal set. The rows of Q form an orthonormal set. Q inverse is also orthonormal because that's just Q transpose. And if you find the determinant of Q, if Q is an orthogonal matrix, then the determinant is going to be plus or minus 1. And just know if it's plus 1, then you say that's proper. And I'll probably explain that later. And if it's -1, then it's improper. If P is orthogonal and Q is orthogonal, then their product will also be orthogonal. Examples of orthogonal matrices is the rotation matrix, change of basis matrix, matrix of a reflection across a line through the origin in R2, and when diagonalizing a matrix for a symmetric matrix, and you are going to get, and that's an orthogonal matrix also. That's it for this lecture. Please watch this a couple of times, and I will see you in my next lecture. Have a good one, everyone, and see you soon.